Hello, let me welcome you to this overview of TOC for inventory management and the underlying theory of constraints principles. The material covered in this overview contains both intellectual and patented property. This quote from Albert Einstein simply provides context. The world we have created is a product of our thinking. It cannot be changed without changing our thinking. As we start exploring the underlying principles of TOC, we can look at the entire supply chain from the end customer to the retailer, to the wholesaler, to the manufacturer, to the vendors, or we can simply focus our attention on the relationships within and between individual links in that chain. From a TOC perspective, we look at a supply chain as a system of systems governed by cause and effect. As a system, TOC recognizes that the organizational processes are not independent processes, but are actually interdependent processes that need to be integrated into an overall operations planning process. And for the overall operations planning process to actually deliver the intended results, execution within each supporting area must be managed so as to maintain alignment with the overall plan. Which brings us to the subject of integration and alignment, which is best addressed through the analogy of a physical chain, where the links represent the various businesses, organizations, and functions that make up the overall supply chain, and the linkages between each of the links are governed by the policies, measures, and information exchange that each of the links uses. And it's the linkages that establish organizational alignment or misalignment. The greater the misalignment, the greater the variability in performance for each of the links in the chain. The policies and measures that cause the biggest misalignments are those that focus on performance of a link within a chain as if it were an independent link as opposed to a group of interdependent links configured to deliver a certain level of overall operational performance, such as resource efficiency, which leads people to process material or information in batches, which then results in delays in movements. Resource utilization often drives organizations to keep people busy producing, which in turn causes more material to be released, which increases work in process, which then causes delays in movement, and other things like volume discounts, economic order quantity, separate P&Ls, and transfer prices can all serve to emphasize performance of a link as opposed to chain performance. Where the biggest set of effects are delays in movement, which leads to more work in process, longer, less reliable lead times, which ultimately delays deliveries, which causes more expediting, and that costs more money. So when we think about inventory management, there are 4 areas that really bring together the challenges, and they have to do with time to resupply, the uncertainty in demand, the risk of being out of stock, and the corresponding investment in inventory. From an operational perspective, the challenges present themselves as delivering on time, delivering with shorter, more reliable lead times, and with lower overall delivery costs in terms of overtime, premium freight, cross shipments, etc. When looking at solutions, you'll find many solutions look to deal with problems more efficiently, such as having real-time inventory information by location so that an out-of-stock condition at one location can be addressed using the available inventory from another location to satisfy customer requirements. The more effective solutions look to address the underlying causes of the problems and in doing so eliminate the problems. And that's the foundation of what we're going to talk about in terms of inventory management and demand-driven performance, which means providing customers what they need when they need it while lowering overall cost of delivery and improving return on investment. The fundamental characteristics of a supply chain are 1. Interdependencies, 2. Variability in both supply and demand regardless of where you are within the supply chain, and 3. The overall performance of the entire supply chain is generally constrained by demand and not capacity. In fact, it's very rare to find a real physical bottleneck, a resource where demand is greater than its available capacity based on a 24-hour workday and 7-day work week. What you usually find are organizational alignment constraints in the form of policies, measures, or information exchange. Given these characteristics, how should we configure and manage inventory in a supply chain? To answer this question, we will begin by examining the types of business problems most supply chain organizations experience. I would ask you to take a couple of minutes to read through the list and make note of those that your organization experiences and their significance. Please press the pause button while you review the list of problems and press the play button when you are ready to resume. I am sure that as you've gone through the list that you also recognize that they are not 15 independent problems, but that they are in fact related to each other in that some problems are caused by other problems. For example, being out of stock, number 5, can cause us to expedite, number 6, and so could having lead times, number 4, that are longer than our customers are willing to wait. And frequent expediting, number 6, can lead to, number 8, workload priorities that are constantly shifting, which in turn can cause, number 7, premium freight charges to be higher than we would like, as well as, number 9, overtime charges that are higher than we would like. When we look at this list of problems in this way, we can see that they're all related to each other, either as a cause or as an effect. And it's probably fair to assume that the variability in demand we experience, number 1, and the variability in delivery performance we experience, number 2, are the two most underlying causes. Using the TOC thinking processes, we would map out the cause and effect connections between all of the problems in our list in order to validate our assumptions that, number 1, the variability we experience in demand, and number 2, the variability we experience in delivery performance, are in fact the underlying causes of all of the other problems on our list. In doing so, we can see that variability in demand or variability in delivery performance on its own as well as together can result in number 6, more expediting. And at the same time, they can both lead to number 11, having too much of some inventories and not enough of other inventories. Too much inventory generally results in number 10, an inventory turnover that is too low. And not enough inventory results in number 5, too many out-of-stock situations for items we plan to stock. And being out of stock can cause us to expedite. Inventory turnover that is too low, number 10, results in number 13, a significant amount of manpower being spent maintaining, preserving, and inventorying the inventory. And each of these can lead to number 14, disagreements over the types and quantities of items to stock, and both number 13 and 14 consume resources. On the other hand, frequent expediting, number 6, will cause number 8, workload and priorities to constantly shift, which in turn can cause number 9, overtime charges to be higher than we would like, along with number 7, premium freight charges being higher than we would like. Number 6, expediting, also causes number 12, inventory designated for one specific order to be redirected to satisfy another order, which in turn can leave us in a position where number 3, we don't always know exactly what we need to process and when in order to satisfy customer demand, which can be further exacerbated by the fact that number 8, workload and priorities keep changing, which can also lead to number 4, lead times being longer than customers are willing to wait, which puts us in conflict with customers, number 15, at least in terms of our lead times. Being out of stock, number 5, and number 3, not knowing what we need to process and when in order to satisfy customer demands, can add to the conflict with our customers in terms of delivery performance. And all of the items in the red boxes, number 9, overtime, number 7, premium freight, number 13 and 14, consumption of resources, lead to increased costs and the need for higher prices, which can result in conflicts around price. It is not surprising to see some of these problems feeding back up themselves like changes in workload and priorities, loops back and adds more variability into our delivery performance, number 2. And longer lead times, number 4, loops back into more expediting, number 6, as well as lower level of inventory turnover, number 10. It appears our initial assumption was correct, and variability in demand, number 1, and variability in delivery performance, number 2, are the underlying causes that we need to address. That leaves us with 2 not necessarily mutually exclusive courses of action. 1, focus our efforts on addressing the causes of variability. 2, focus our efforts on nullifying its effects. Given the fact that we will likely never totally eliminate variability, we're usually better off focusing our efforts first on removing the causes associated with organizational misalignments while nullifying the effects of process and resource variability in order to stabilize overall business performance. Only then, using the information gained from having nullified the effects of process and resource variability to identify and address the causes. This type of approach will realize the greatest improvements in performance. With that understanding in mind, we'll focus our attention on how do we most effectively nullify the effects of process and resource variability. When we think about the question of what's the most effective way to identify and nullify the effects of variability in delivery performance and demand, it brings us back into the planning process in terms of how well it aligns and integrates from an execution management perspective. From a planning perspective, it requires a planning process that accounts for demand, process, and resource variability when establishing inventory levels or determining reliable lead times. And from an execution management perspective, it requires that we are able to adjust priorities based on the impact that actual to plan movement will have on delivery performance. To better understand how inventory planning and execution management should integrate, let's start with an example that shows daily demand for an item on a timeline, where the daily demand is variable and is as low as 0 and as high as 5. In the lower left is a graph showing the range and distribution of variability in our lead time, from as short as 1 day to as long as 10 days. If our focus were on identifying and eliminating the underlying causes, we would likely find them in the areas of process variability, product mix changes, quantity and timing, resources not readily available, either busy working on something else or because of planned or unplanned absences or breakdowns. But as we said earlier, our focus is first on nullifying the effects of variability in demand and delivery performance and then eliminating the causes. Nullifying the effects of variability in delivery performance requires that we establish a lead time that can accommodate a large part of the variability. The first thing we have to consider, at least in terms of our thinking, is that we have a tendency to look at the world from the perspective of averages, which in this case is 5 days. Using a 5-day average lead time, what percentage of the time would we be wrong? Most of the time. Given the distribution of lead times, the actual lead time would be longer or shorter than the average most of the time, and half of the time it would be greater than 5 days, which means half of the time we would be adversely affected. Here's where we need to shift our thinking from an average lead time to a reliable lead time, something that would accommodate at least 95% of the occurrences, and in some cases even more than 95% can be required. A 95% reliability would take the lead time from 5 to 7 days and 100% reliability to 10 days. So a reliable lead time is actually the planned period of time between placing and receiving an order that is very often greater than and seldom less than the actual time required. For our example, we will use a 95% reliable number, which equates to 7 days. The other side of integrating planning with execution management has to do with deciding how we are going to manage replacing inventory, which has been consumed or sold, and incorporating that decision into the planning process when establishing reliable lead times. We decided we're going to replenish according to usage, which means if we consume 2, we will replenish 2. If we sold 6, we will replenish 6. And that will be the basis on which we set inventory levels or buffers and manage replenishment. As we look at daily demand through our 7-day window of reliable lead time, we see a pattern of daily demand, 1, 2, 4, and a 1, that accumulates to a quantity of 8. So as we move our 7-day window forward in time to the next daily demand, we see another pattern of daily demand with a cumulative total of 9. And when we move forward to the next demand grouping, we have a cumulative demand pattern of 7. And we move forward a couple of demand groupings, and we have a cumulative pattern of 10. And if we process through all of this demand data in the same manner, using our 7-day window of reliable lead time, we will be able to determine each maximum accumulation of demand, the number of times they occurred, as well as the upper limit, which in this case is 17. If we transfer the cumulative demand for each window of reliable lead time back to the original timeline on which they occurred, we would get what's called the time-based demand pattern, where each vertical bar represents a cumulative demand in that 7-day window of reliable lead time along the demand timeline. With this type of visual representation, it's very easy to see how much inventory we would need to replenish in each window of reliable lead time, which is what brings together demand variability with the time to reliably replenish, while defining the upper limit on inventory levels and the risk of out-of-stock conditions, both quantity and timing, resulting from a decision to operate at reduced inventory levels. If the demand used to establish these time-based demand patterns contained customer unique identification information, it would be possible to identify which customers would most likely be impacted by these out-of-stock conditions. As opposed to processing demand using complex algorithms that few people understand to establish inventory levels, time-based demand patterns bring together variability in demand with variability in supply in a way that enables simple and effective pattern-based decision-making on inventory investments versus the risk of being out of stock at a stock-keeping unit level or part number level. We now have a baseline using the daily demand with a 7-day reliable lead time and a resulting inventory upper limit of 17, from which we can perform what-if analysis to determine the impact of lead time reductions on inventory levels. By processing the same daily demand with a 4-day reliable lead time, we can see the upper limit on the inventory decreases from 17 to 12. The other side of the equation impacting inventory levels is variability in demand. The question is, can we do anything to effectively reduce demand variability, whether it be quantity or timing, without reducing overall volume? And if we could reduce demand variability, what impact would it have on inventory levels? Sometimes demand variability is a result of things like volume discounts, where the customer demand we experience is more reflective of achieving discount quantity targets than it is of their actual daily usage. What we'd like to know is what impact would reduced demand variability have on our inventory levels. By adjusting daily demand to be more reflective of actual customer use, we could determine the impact that smaller, more frequent customer orders would have on inventory levels and use that information to establish a more effective customer interface. By processing the adjusted daily demand with a 4-day reliable lead time, we can see the upper limit on inventory decreases from 12 to 9. The TOC solution for inventory management uses reliable lead times in conjunction with demand variability to establish inventory levels, or buffers, that effectively decouple supply and demand variability and initiates replenishment in accordance with actual use, and in doing so integrates planning with execution management. When we look at applying the TOC inventory management solution to protecting part or all of a supply chain from supply or demand variability, the focus is on locating properly sized inventory buffers. If we were managing a manufacturing or repair business, we could be looking at establishing inventory buffers that protect against supply or delivery performance, in which case we would be managing the buffer of inbound materials. If we were managing a retail business, we would be looking at having inventory buffers of products on the shelf sized to capture sales given the variability in customer demand and the time it takes to reliably replenish the shelf, where the time to reliably replenish has the same definition as reliable lead time. Or we could be looking at a more extended supply chain going from a retailer back to a wholesale distributor with inventory buffers at the distributor, decoupling supply and demand variability between those two businesses, as well as reducing the lead time to replenish the retailer. And we could extend the solution all the way back to the manufacturer and their supply base, providing raw materials used to manufacture products which are sold to the wholesaler, who in turn sells them to the retailer, who then sells them to the end user. The other aspect of physical inventory buffers is that when properly located and properly sized, they can be used to significantly reduce overall lead times to the customer. Buffer sizing establishes a clear connection between inventory levels and replenishment time, given the variability in customer demand and how it aggregates back and the time to reliably replenish from the previous link. And the initial buffer size determination is based on the maximum expected demand during the time to reliably replenish, from which we can then use time-based demand patterns to assess the inventory investment versus the risk of being out of stock. When you break down the time to reliably replenish, there are two major time blocks. The first is the reliable replenishment interval, RRI, how often are orders being placed or released, which could be daily, weekly, every other day, or at some other time interval. And the second is the reliable replenishment time, RRT, that takes into account the time required to complete all of the process steps to purchase, manufacture, or repair, and the variability associated with completing those steps as planned in order to establish a reliable replenishment time. Combining the time estimates for reliable replenishment interval and reliable replenishment time establishes the time to reliably replenish, the TRR. Let's assume the demand represented in each of these four graphs is for the same product from 4 different customers. What we see is that demand patterns differ by customer. Aggregate demand for all 4 customers would be variable over time, and the risk of being out of stock increases with peak demand exposure. To get a better understanding of how buffer sizes are calculated, let's assume the demand patterns in these graphs represent 4 different products, A, B, C, and D, and the time to reliably replenish is 3 days. As you look at each graph, visualize the block width of each demand as representing 1 day, where the total time span in each graph covers 10 days, with some days having 0 demand. Which means product A has 6 out of 10 demand days, and product B has 8 out of 10 demand days, product C has 5 out of 10 demand days, and product D has 5 out of 10 demand days. So for product A, what's the maximum cumulative demand in a moving 3-day window of time to reliably replenish? We see 20, 0, and 10 equals 30, 10, 0, and 20 for 30, 20, 0, 0 for 20, and 10, 20, and 10 for a maximum of 40. What about product B, which has a much more uniform demand? Here the maximum is 30, comprised of 10, 10, and 10. What about product C, which has even more variability in demand? The maximum is 60 from 50, 0, and 10, or from 10, 40, and 10, and goes as low as 0 between the two 10s. What about product D? It could be as low as 10, and we also see 60, then 50, then 30, and the maximum being 70, 20, 0, and 50. And that's how we accumulate demand in windows of time to reliably replenish to determine the upper limit on our buffer size to minimize out-of-stock conditions. In this example, the graphs represent demand from 2 different customers for the same part number or stock keeping unit, which is being supplied from the same inventory buffer and has a 3-day time to reliably replenish. In order to determine the upper limit on the buffer size, we first have to aggregate the demand coming from both customers, which produces a different demand pattern that is also variable over time. And then we process the aggregate demand using our 3-day time to reliably replenish, where we see 20, 50, and 10 for a total of 80 in the first 3-day grouping, and a maximum of 100 made up of 20, 60, and 20 in the last 3-day grouping. As we've seen, determining buffer size is a function of demand variability and time to reliably replenish. So what impact will a 33% reduction in time to reliably replenish have on buffer size? Will the size of our buffers decrease by 33%? For product A, a 3-day time to reliably replenish gave us a buffer size upper limit of 40. A 2-day TRR gives us an upper limit of 30, which is only a 25% reduction. For product B, a 3-day TRR gave us a buffer size upper limit of 30, and a 2-day TRR gives us an upper limit of 20, which is a 33% reduction. For product C, a 3-day TRR gave us a buffer size upper limit of 60, and a 2-day TRR gives us an upper limit of 50, which is a 17% reduction. And for product D, the 3-day TRR gave us a buffer size upper limit of 70, a 2-day TRR gives us an upper limit of 50, which is a 28% reduction. What does this tell us? The more uniform the demand, the greater the likelihood of a one-to-one relationship between time to reliably replenish and inventory levels. And the more variable the demand, the lower the likelihood of a one-to-one relationship between time to reliably replenish and inventory levels. For example, what if we further reduce the TRR from 2 days to 1 day, a 50% reduction? What would be the change in our buffers? For product A, a 2-day TRR gave us a buffer size of 30, a 1-day TRR gives us a buffer size of 20, a 33% reduction. For product B, a 2-day TRR gave us a buffer size of 20, and a 1-day TRR gives us a buffer size of 10, which is a 50% reduction. For product C, a 2-day TRR gave us a buffer size upper limit of 50, a 1-day TRR gives us an upper limit of 50, a 0% reduction. For product D, a 2-day TRR gave us a buffer size upper limit of 50, a 1-day TRR gives us an upper limit of 50, once again a 0% reduction. The overall process of buffer sizing using time-based demand patterns starts with input data, which includes daily historical demand for each part number or stock keeping unit for a period of time sufficient to establish a clear picture of demand over time, including any market, seasonal, or operational changes, and a TRR for each stock keeping unit or part at each buffer location. Then processes the input data by summing demand in windows of TRR to determine the cumulative demand in each window of time to establish the upper limit for an initial buffer size, from which adjustments can then be made for seasonality as well as trade-offs between investments in inventory and out-of-stock conditions. The result is a buffer size for each stock keeping unit or part number at each buffer location in the supply chain. As we said earlier, the TOC inventory management solution can be applied to protect part of a supply chain or all of a supply chain from supply or demand variability, or to significantly reduce overall lead times to customers. In either case, properly located and sized inventory buffers that are managed using TOC replenishment principles achieve the best results in terms of reducing out-of-stock conditions and improving overall inventory turns. Where buffer sizing establishes clear connections between inventory levels and replenishment time, given the variability in aggregated customer demand and the time to reliably replenish from the previous link, initial buffer size determination is based on determining the maximum expected demand during the time to reliably replenish, from which time-based demand patterns can be established. And time-based demand patterns bring together variability in demand with variability in supply using reliable lead times in a way that enables simple and effective pattern-based decision-making by which to assess trade-offs between investments in inventory versus the cost of being out of stock at the stock keeping unit or part number level. Time-based demand patterns provide a viable human alternative to the numerical answers obtained from complex algorithms that very few people understand. So if you think time-based demand patterns could help you and your organization do a better job of locating and sizing inventory buffers so as to improve availability, reduce out of stocks, and increase inventory turns, and would like to experience what this patented technology could do for you using your own data, please contact us by email at analyze@goldrat.com or by phone at 203-624-9026. If you'd like to see a more detailed working example of the TOC inventory management solution, where planning and execution management come together to form a closed-loop process, please view the buffer sizing exercise.